We've been talking about vector valued functions, and this is how we're looking at a vector valued function. This is our abstract notation for it. So today we're going to take derivatives and integrals of vector valued functions and see if we can try to find some meaning to that. And without going through all the technical stuff that they went through in the book, let's take a look at the derivatives of vector valued functions. Most of the time people just say vector functions, but I don't know. Saying vector valued function seems a little longer. So when we took derivatives back in Calc 1, we took the derivative with respect to the independent variable, right? The input variable. So in or for functions f from R to R, from a real number to a real number, that usually, in terms of our standard notation, we usually take x your input and your y as your output. We say we take the derivative with respect to x of that function. And so there's a lot of ways to take the derivative of these things. Well, there's one way to take the derivative of these things. A lot of notation is what I meant to say. There's a lot of different ways of writing your derivative, df, dx, dy, dx, or y prime, or whatever. But what's important to point out is that derivative with respect to the independent variable, or the input variable, we're taking the derivative with respect to the input variable. And then your output variable is whatever your output variable is going to be, and it's your derivative. So if we take a look at now our vector valued functions, for our vector valued functions, what is our input variable? The parameter t. So if we were to take the derivative of vector valued function, we would say we would probably want the derivative of the vector valued function with respect to t. So we would say d dt of the vector valued function. So just to shorten the notation, we'll just call that r prime, which is to say the derivative. And since there's only one variable that we're dealing with, you know it's a derivative with respect to t. So now the question is, how's this going to look like? If we look at how the r of t looks like, it's a vector valued function in vector form. We see the components for the x, the y, and the t. And so what would make the most sense in taking the derivative with respect to t here? And just take the derivative of each component. So that's exactly what's going to happen. So we take your x prime, or your x of t, and take the derivative of that, because it's a function of t. And we have your y prime and your z prime. And then now we have the derivative of these things. So the book goes through the whole proof of the derivative. The definition of the derivative is some limit as h approaches 0 kind of business. So I don't think we need to go through that business, but that's a general idea for the derivative. Okay? So we're done. I suppose we should do an example. That's what you guys are waiting for, right? So let's do an example where we're looking at probably one of our most popular curves that we're going to be studying is the helix. So let's let r of t equal to cosine t, sine t, and just t. Let's put a multiplier. Remember, just for the sake of being able to see this in the picture, I usually like to put a multiplier here. 1/2, no, something less than 1, right? So let's 1/5, 1/10, 1/5. So let's just put 1/5 t. So let's take the derivative of this. R prime of t is equal to, it should be easy, right? And then 1/5. So that's easy, right? So that's the math part of it. Yeah, so that's the other half, the geometry part that I think should be a little bit more interesting. So let's figure out what this looks like. And what's going to be strange about this is that it's not going to be very meaningful to look at the derivative like this. I mean, it is. There's a lot of really important information in the derivative, and so let me rephrase that. I didn't mean to say that it's not meaningful, but it would be strange to look at this as a function. I don't know if that makes any sense either, but let's see how it goes. So let's take a look at our cosine t, sine t, and 1/5 times t. And let's make this more significant. Let's go all the way to 4 pi so that we see a good chunk of that helix that we're talking about. Now, if we were just to take the derivative and kind of naively and blindly put the derivative down here, not very helpful. It's just that blue circle. If I look at this, this is really just the sine and the cosine and the x and y components, which draws a circle, right? And the direction might be different. But here I have a constant 1/5, which means when z is equal to 1/5, well, z is going to be equal to 1/5 the whole time as you're drawing the circle. So that's just a circle that's being drawn, and if we went from 0 to 2 pi, probably, or to 4 pi, it probably got drawn twice. So that's not very significant for us. It's not a very informative piece of geometry. So, any suggestions on how to deal with this? All right, well, let me, as one suggestion, let me go back to the equation of the helix itself.
Can you add some constants to that? Is that what you mean? Like, what can I do to it to make it more apparent of what's happening?
Well, that was a question. I don't know if adding constants would do it. But what I'm going to do is I'm going to take a look at I'm going to take a look at my position function, the r function, with the cosine, the sine, right, and then the 1/5 t. And I'm going to use a slider. So I'm going to make this vector and if I use the original R function, the R function, remember, is a vector that draws the helix itself, right? So the original vector is, if I were to take a look at that as a vector, that's a vector that draws a helix. So maybe instead of looking at the derivative as a function, we can take a look at the derivative as a vector and see what happens with that. So I'm going to change, instead of looking at this function over here, I'm going to change this to make it look like a vector. Do you understand what I mean when I say that? So let's take a look at this as a vector. And then let's change this to slider A. Okay, let's see if this vector seems more significant now. And we have to focus on the vector. Can you tell between the black and the blue? The red was better. So let's get the slider out again and slide it around. All right, that red vector isn't really doing much for us, is it? It's tracing out that blue circle that I took out, right? So that's still not that significant. What if I tell you that that vector was really significant? What should I do with that vector to make it make sense in this drawing? Any ideas? Remember, a vector has a direction and magnitude, and it doesn't matter where it is in space. I can move it around, and it will still have a direction and magnitude.
You're finding the tangent to a point?
What?
You're finding the tangent and the point where the original vector is pointing?
Yeah, well, so what should I do with that vector?
Like from something.
No?
Have the tail start from when the head of the actual helix vector.
Yeah, so what if I take that vector and then move it so that its tail is where the position is pointing? Let's see how that works out. So I'm going to take my red vector. Actually, let me keep... Yeah, let me keep that red vector. And let's go to the position. Instead of starting at 0, let's go to this position where the vector actually is. So this is my position vector. And one more thing about this graphing calculator is that you want to make sure that you add that to the position vector. So this is actually a vector that goes from the first point is the tail, the second point is the head. So I don't want to be pointing where it was pointing when the tail is at 0. I want to be pointing where the tail is wherever the tail is. So let's see if this is any better for us visually. So look at the blue. Can you tell the blue vectors?
Yeah.
So this is the velocity vector in standard position. This is the velocity vector. Oh, I'm calling it the velocity vector already. It's the derivative vector in standard position, the derivative vector that's moved out of standard position so that its tail is where the point is supposed to be, the position. And then this is our position vector right here. And you can see that as we move the position around, that velocity vector, the derivative vector, is always tangent to the curve. So that's the significance now. So if we just take away that red vector and just focus on the velocity vector that's been moved so that its tail is at the position vector, we have a tangent vector. Pretty cool, huh? All right. So what's all that mean? That means we can find the tangent vector. So this we'll call the velocity vector or tangent vector. Let's call it the velocity vector. Is a vector that's tangent to the curve at any point t. So if we pick a specific point to see where it's tangent to, then that's its tangent to that point. So this is the graph of it. Let's see if we can actually do some computations. Let's take a look at r of, let's say r of pi. R of pi is going to be, what's cosine of pi? -1. Sine of pi, 0. And this is 1/5 pi. R prime of pi is equal to, what's sine of pi? 0. And then cosine is -1. And this is just 1/5. So in general, I want to look at the position vector as a point. You can also look at it as a vector from standard position. But in general, I want to look at this as a point. And then I want to look at the velocity, the derivative vector as a vector. So maybe you want to write it like that just to make sure that you want to look at it as a vector. And then move that vector so that its tail is at that point. Then you have a tangent vector. Okay? So, is this okay?
Yeah.
All right. So, let's play a game. Oh, I don't know about games. Give me an angle between
60.
between 0 and 2 pi. 2 pi over 3. Okay, so you're on a roller coaster, and let's be in space here so that we don't have any issues about gravity. And let's say there are 4 walls in this roller coaster that you're in space. 4? Yeah, let's just say there's 4 walls. There's a wall where you have x is equal to 5, x is equal to -5, y is equal to 5, y is equal to -5. Okay? And let's say 2 of these walls, which 2 walls? Let's say these 2 walls have spikes on them. And let's say that these 2 walls have Velcro on them. So you're on this roller coaster, and then Jessica presses eject when t is equal to pi over, or 2 pi over 3, and then you go flying off the roller coaster at a tangent line. Yeah, so the question is, do you, in your Velcro suit, do you get stuck on the wall, or do you die? Okay? So that's the question. So what I want you to do is I want you to try to be able to find an equation of a line that comes from this, this where you get ejected. And then, so at that point where you get ejected is going to be your initial point. So find line with point, with some point. What's the point going to be? What do I need for an equation of a line? Don't say point and slope. What's an what do I need for an equation of a line? Point and direction. Okay? We need a point and a direction. So the point that you get ejected is at time 2 pi equals 3. But what is the point going to be? Into where?
It's wherever that r of t is 2 pi over 3.
So in math, we say r of 2 pi over 3. And we said we needed a direction also. What is the direction here?
At 2 pi over 3.
It's the derivative at 2 pi over 3.
R prime of 2 pi over 3.
R prime of 2 pi over 3. Okay? All right. So why don't you guys come up with that equation of a line. Meanwhile, I'm going to fiddle around here and mess around with my graphing calculator program to see if I can set all this stuff up. Then you guys can give me the answers. I should pause the video, huh? It's just kind of running. All right, let's figure it out. So we'll find the equation of the line. We'll find the direction and point, find the equation of the line, and then we'll do some figuring out which direction this is going. So at 2 pi over 3, so we need to find our point. Our point is when we put 2 pi over 3 into the cosine and sine. So cosine of 2 pi over 3 is -1/2. And then root 3 over 2, positive? And 2 pi over 15. So this is your point. This is the point that you're in. Your direction is going to be the derivative. Remember that the derivative was? So what is it? Negative? Okay. So our equation of the line I guess I'll call it L of t. Oops, turn blue. Is going to be equal to, what's it going to be equal to? So point plus t times the direction, and the point is this, and t times the direction. Let me write it kind of like in vector form where the x and the y and the z are separated. So the x is going to be negative 1/2 minus root 3 over 2 t. The y is root 3 over 2 minus 1/2 t. And then the z is 2 pi over 15 plus 1/5 t. So by writing it in, I could have written it horizontally, and then that just means each component is your x, y, and z, or you can write it vertically, and you can see the components. So we don't care about the z-axis. These are walls infinitely going up and down, and but we do care about where it's going to hit. So it's going to hit either at x equals 5 or y equals 5. So the thing to probably do is to try to figure out when each of these are equal to 5. So let's take 1/2 minus root 3 over 2t equal to 5, and then solve for t. So let me solve for it just by using the algebra thing, and then you guys can give me an actual number here. So it looks like it's 5 plus 1/2 divided by negative root 3 over 2. Can you guys give me a t value for that? Negative 6.35. So it's going to take negative 6.35 for this thing to hit the, which one did I set? To set x equal to negative 5. So the fact that it's negative probably means that's not the direction I want, right? Because I got this equation. It goes from this point in this direction, and that's going to be, it's going to draw it in a positive direction where t is positive if you're going to go in this direction. And if you got a t negative, then that's looking at it backwards. So this is not, it's not going to hit the wall, not going to hit x equals 5. So let's try the y equals 5. Oh, by the way, if this is negative 5, would it hit? Not necessarily. Let's try the other one. Y equals to, what's the y equal to? Root 3 over 2 minus 1/2 t equal to 5. So here t equals 5 minus root 3 over 2 divided by negative 1/2. And what is this guy equal to? We got something? Say it again? Negative 8.27. So it's not going to hit that either. Because it's negative, and we got this thing pointed in a direction of whatever this direction is. And so when we get a negative value, so the negative value is saying that your line is going backwards. So it's not either of those. Let's try the negatives. This is going to be a long page. X equals -5 this time, -1/2 minus √3/2t equals -5. So t equals -5 plus 1/2 square root of -√3/2. And what is this? 5.196. So this looks like it would be it. But the thing is that, yeah, if this is going to go in an angle, it's a possibility that it would hit two walls if our walls go infinite. So let's figure out our y value for this, or our y if it hits the y value, y equals -5 plane. So y is √3/2 minus 1/2 t, and we'll set that equal to -5. And so in this case, t equals -5 minus √3/2 divided by, -5 minus √3/2 divided by -1/2, 11.7. So it looks like this graph will eventually hit the y equals -5 plane, but will hit it further out along the line. But it will hit, it'll hit the x equals -5 plane first before it hits the other one. Okay? So let's take a look at the graph. Let's zoom out a little bit so we can see. Oops, not in, zoom out. So we see that this vector, the yellow planes are the spiky planes, and then the black and white planes are the planes that you hit. So if you can see this point is going to hit the plane here. Can you guys even see the line? It's going to hit that plane, and then eventually, if this plane were to go out further, it'll hit this plane also. But it won't hit it until time 11 seconds or whatever it is that we're measuring. So this is our picture for this drawing. Is that okay? That would be a good graph. All right. So let's see what I just said. T is equal to, what is it, 5 point what? 6. You hit the x equals -5 plane. That's this plane right here, x is equal to -5. And eventually, somewhere along the line, you'll eventually hit the y equals to -5 plane. So that gets hit at around 11.7-ish. And then those other two planes that we got where it was negative would be if the line went backwards. And going backwards, we'll see that we'll hit the other two planes. Okay? Pretty cool, huh? So, I like these problems. Unfortunately for you, you'll have some stuff like this on the test. All right, so this is a tangent vector. It turns out that no, this is probably something you guys are going to talk about. So it turns out that the tangent vector has a direction, and it tells you which way your particle is going to be moving tangent to the curve. But remember, a vector has a direction and a magnitude. So the magnitude of this tangent vector happens to be also important. By the way, when I put the vertical bar, single bars, it's the same as double bars, right? And that is the magnitude. Okay. Did I press play again? Resume? Yeah. And the length of the tangent vector happens to be important because, did you guys talk about this in physics somewhere? It's the speed. So it turns out that the speed is a numerical value, it's a scalar value that tells you how fast something is going. And the tangent vector has more information in that not only does it have that length of the speed, but it also tells you which direction it's going. Now, in calculus 2 or 1 or whenever you guys started to, the ball throwing up in the air and when does it land, what's the maximum height, that kind of business. That sort of problem is a problem, it's a one-dimensional problem. It goes up and goes back down, so you only have a one-dimensional movement of the ball. When we're dealing with, when we have vector-valued function, now you have all the movements of the ball. You can go in 2 dimensions, you can even go in 3 dimensions to talk about the tangent vector and the speed and all that stuff. So the speed used to just be the derivative, and if it's positive, it was going up. If it's negative, it's going down, right? That was back in Calc 2. That's how you figured out how fast the ball was going when it hit the ground. Over here, the speed now is not just the absolute value of a scalar because our vector, our tangent vector is no longer a scalar, it's actual vector. So the speed is going to be given by the magnitude. Okay? So, how fast were you going when you hit the wall? Assuming that your speed didn't change, you're in space, right? You got ejected off the roller coaster, and you went on this constant speed until you hit the Velcro wall. Good thing it wasn't the spike wall. So how do you calculate your speed for that example? Just magnitude of the tangent vector. So let's find our tangent vector. If you remember what that was, this is specifically at that point, right? At 2 pi over 3, and this is the derivative. So that, you remember what that was? It was like -3 over 2, negative 1/2, and 1/5. And so the magnitude of that is just each of these things squared all under square root. So root 3 over 2 squared plus 1/2 squared plus 1/5 squared. And I don't care about this number, but can you just tell me what the answer is? Say it again? 1.02. So I haven't been putting units on there, but if you put units, this is the speed, something per something. So feet per second, miles per hour, whatever. Okay? All right. So tack on another formula to try to remember. We got the tangent vector being tangent, the velocity vector being tangent to the position, and then the speed being how fast your particle is moving. Okay? All right. See, can I milk this problem some more? Yeah, there's an acceleration. Oh, I need to talk about the unit tangent. So sometimes, like in this case, it really didn't matter how fast you were going. So the speed didn't really matter. What's more important is that you have the direction. And a lot of times when the magnitude doesn't matter and you just care about the direction, we usually like to make our vector a unit vector. Okay? So let's come up with what's called a unit tangent vector. Let's do that in the next page. So it's really just a simple formula, right? What do you do to make a unit vector? Divide by the magnitude. So we'll take a velocity vector. Remember that r prime of t is your velocity. And the velocity vector is tangent. And so now to make this into a unit vector, you just divide by its magnitude. So you take r prime of t, you divide it by the magnitude of itself, r prime of t, and then now you have your unit tangent vector. Okay? And it turns out that the helix is a nice way to find the unit tangent vector. A lot of times in general, we usually want to keep this as a function of t, because as you're moving along your curve, you're going to want to compute the unit tangent normal or unit tangent vector when you're moving along the curve. So sometimes they call this capital T of t. As the tangent vector. Okay? All right. So there's also that acceleration vector, right? And so just like the acceleration back in Calc 2 or in physics that we've learned, that's just the second derivative. So let me put that as an aside here. Okay, and for now, that's all I'm going to say about it. Tomorrow, I'll have a lot more to say about the acceleration vector when I combine this idea of a unit tangent vector, and then there's going to be, we're going to create a frame moving along a particular curve called the Frenet frame that will involve three unit vectors. Okay? All right, now, if we could take derivatives of vector valued functions, we should also be able to take integrals as well, right? Should. So for 5 minutes, we got 5 minutes left, let's take integrals of stuff. Now, the integral was first defined to you as areas of rectangles and things like that. That idea of the integral for vector valued functions isn't going to make sense to us anymore. But we do have indefinite integrals, right? So if we have a vector valued function r of t, and we know that the independent variable is t again, and so we can take the integral with respect to t of that, and let's do this as an indefinite integral, then it kind of makes sense to just take the integral of each of the components again like we did last time, right? So each of the components is a function of t. And so it makes sense for us to be able to take the derivative or the antiderivative of each of those components separately. Okay? Now, the only thing that might be weird about this is that if we're talking about an indefinite integrals, when you guys had your integrals exams in Calc 2, what is the one thing that you need to remember to put for indefinite integrals? Plus c, plus they generate a constant, an arbitrary constant, because this is a family of functions, and so we need to generate a family of constants. So a lot of times, I personally like to think about the constants as being constants added to each of these components. So whatever the integral is for the first one, plus c1, comma, whatever the integral is, plus c2, comma, whatever the integral is, plus c3. That's usually how I'd like to think about it. And then what this is going to do is going to have three different constants that I have to worry about. But in the textbook, they take the integral of the first, and then you just find some antiderivatives for the components. And then what they do is they add on a constant vector on the outside. Okay, and that constant vector, essentially, to match up with the way I like to do it, is just c1, c2, c3 as a constant. So just remember that when you're taking an indefinite integral, there are constants that you hopefully would be able to solve for. But in general, an indefinite integral is going to come up with 2 or 3 constants depending on how many components you have in your space. All right? Okay, so the rest of the calculus behind this is pretty simple. I don't think there's any definite integrals that you don't have to worry about it for these vector valued functions at least. So, hey, you still got like 3 minutes. All right, well, I think that's all I have to say. You guys